My name is Sydney ASMR, and I'm about to eat some chocolate. That was a milk chocolate truffle. But now I need some water. Now, I am a nursing student. It is my first ever experience in college, and it's all online. And one of the classes I'm taking is A&P1. A&P1. And my class is separated in between lectures in my labs. And today I'm going to go over some lectures. Primarily I'm going to stay on the nervous system. I just had a test over it and I did well, but I still feel like I need to study a little bit because we have an upcoming final. And so, why don't you study with me? I am by no means a professional. Half the time I don't know what I'm talking about. I'm just trying to remember information to get an A on a test. But consider this like a role play video where you're studying with Sydney. So, let's begin. I'm going to pull up my teacher's notes. We're going to go to Canvas. 2020. This is school, everyone. We're going to Canvas online. We log into our personal account. We go to our courses. And then we go to Anatomy and Physiology lectures. And we're going to go to modules. And then we're going to go to chapter 12. And we're going to be going over nervous tissue first. Let's go over some of the basics. Sense organs and sensory nerve endings receive information and transmit messages to the CNS, otherwise known as the central nervous system. The CNS processes the information and determines a response. The CNS sends a response to muscles and gland cells. Alright, let's talk about anatomical subdivision. The peripheral nervous system, otherwise known as PNS. It is like the nerves and the ganglia. Now, nerves are a bundle of axons wrapped with connective tissue, and a ganglia is swellings in a nerve where somas are centered. Functional PNS divisions. So we have a sensory or afferent with an A division, which carries signals to the CNS. So afferent sensory to the CNS. We have the somatic sensory division, which carries signals from receptors in skin, muscles, bones, and joints. Then we have the visceral sensory division, which carries signals from the viscera of the thorax and abdomen. Then we have the other functional PNS division, known as the motor efferent with an E division, which carries signals from the central nervous system to effectors. So, E efferent motor, it carries signals away, as where afferent sensory carries it to the CNS. parasympathetic division. The these are very hard words. Sympathetic division arouses the body to action, also known as your fight or flight mechanisms. Then you have the parasympathetic division, which has a calming effect. It's where you rest and you digest. So sympathetic is where your fight or flight action comes into play, and then your parasympathetic division has a calming effect. Alright, then we have our properties of our neurons. We have some universal properties. Excitability, conductivity, and secretion. Let's talk about excitability. This is where you respond to environmental changes, aka stimuli. Then you have conductivity, where they respond by producing electrical signals that are transmitted to other cells. So it's when a cell is able to easily conduct energy to another cell. Then we have secretion, where a neuron releases a neurotransmitter, kind of like ACH, acetylcholine, to stimulate the next cell. Then we have functional classes. So we talked about sensory afferent, which means to the central nervous system. The sensory neurons detect stimuli and transmit information to the CNS. Then we have interneurons or association neurons, which detect stimuli and transmit information to the interneurons, which make decisions. So the interneurons make decisions and also connect sensory and motor pathways. So interneurons, it's kind of connecting, they make decisions. Alright, then we have the motor efferent, which sends signals from the central nervous system. Alright, let's talk about the structure of a neuron. So let's talk about a motor neuron. So you have the soma. That's the cell body. It's a control center containing the nucleus and the organelles. Then we have dendrites, which are the branches, the branch processes arising from the soma. They receive signals. Then we have the axon hillock, which is the attachment of axon on the soma. Then we have axon, a process that sends signals. It sends signals away from the soma. Alright, then we have supportive cells, also known as neuroglia. So, we have some complicated words coming up. We have oligodendrocytes. These are cells with processes that form myelin, which insulates the axon in the brain and spinal cord. Then we have ependymal cells. They're cuboidal cells lining the cavities of the brain and spinal cord that secrete and circulate cerebral spinal fluid, which is found in our brain and our spine. They're I found out today, actually, we have a lot of cerebral spinal fluid in our brain, and if it weren't for that that fluid, just like encapsulates the brain, and inside the brain, it would literally crush like our neck, and we'd be dead. Okay. We also have, so first of all, we're talking about cerebral spinal fluid, and what makes that? The ependymal cells, what I just talked about, they're cuboidal cells. Okay, now we have microglia. These are your immune system cells. Then you have astrocytes. They form a supportive framework and blood-brain barrier. Then you have Schwann cells. They insulate axons of the PNS, the peripheral nervous system. And then you have something called satellite cells, which insulate somas of the PNS. So Schwann cells insulate axons, satellite cells insulate somas. Let's talk a little bit more about the myelin sheath. The myelin sheath itself is an insulating layer around an axon. In the PNS peripheral nervous system, a Schwann cell, which is what encapsulates the axon, spirals repeatedly around a single axon. Alright, let's talk about endoneurium. This is a thin sleeve of fibrous connective tissue that covers the Schwann cell. axons of multiple neurons. And from if you guys can remember, an oligodendrocyte is a cell with processes that form myelin. Okay, let's talk about regeneration of nerve fibers. A damaged peripheral axon may regenerate if its soma is intact. So if the soma is intact, a peripheral axon can regenerate. Let's talk about the electrophysiology of neurons, which is just a long fancy word for how a neuron has electric capabilities. So we have neural communication is based on electrophysiology. So the ability for neurons to communicate with each other is through electricity. An electrical potential is a difference in the concentration of charged particles between one point and another. So I just read that. I don't even know what I just read. So let's read it again. An electrical potential, so the chance of electrical currents happening, is a difference in the concentration of charged particles between one point and okay. I understand. So two different neurons with different charged particles. This is what allows information to be shared. So let's talk about the resting membrane potential. Electrolytes are unequally distributed between the ECF and the ICF, which just means the inside of a cell has a negative charge, as where the outside has more of a positive charge. So there's more K plus, aka potassium, inside, and more Na plus sodium on the outside, and that's why there's a difference. And this is where the electrical potential happens, because two different areas have two different charges. This is where the saying opposite attract come in hand. This is where you get the NAK pump. And this is what allows neurons to get energy or electricity so that they can communicate. The NAK pump maintains the RMP at negative 70 MV. Alright, let's talk about some local potentials. Neurons can be stimulated by chemicals, light, heat, or mechanical distortion. Upon stimulation, sodium channels open and sodium flows into the cell toward the trigger zone in the axon hillock. And remember, the axon hillock is simply where the axon and the soma connect. Alright, so depolarization is a membrane voltage shift to a less negative value. So when something becomes less negative, it becomes depolarized. Let's talk about local potential, or characteristics of local potentials. So it can be graded, decremental, and reversible. Graded, which means they vary in magnitude according to the strength of the stimulus. So if you have a really strong stimulus, it could be a strong local potential, or it could be, if it's a small stimulus, it can be a small change. So it's graded. Then it can also be decremental. They get weaker as they spread from the point of stimulation. Just, basic electricity. Electricity isn't forever. It has to keep getting stimulated. And it can also be reversible. If stimulation ceases, the cell quickly returns to RMP, which is resting membrane potential. Alright, action potentials, or AP. AP occurs when a local potential spreads all the way to the trigger zone, which is near where the axon hillock is. Alright, so there's something called hyperpolarization, where more more potassium leave than sodium enters, causing the membrane voltage to dip below resting membrane potential. Na and K switch places, or I should say sodium and potassium switch places, using sodium potassium pumps. Alright, let's talk about some characteristics of an action potential. All or none. The neuron always and only fires if the stimulus depolarizes the neuron to threshold. So if the stimulus doesn't depolarize, it won't happen. reversible. If the neuron reaches the threshold, the AP goes to completion. So action potential and local potentials are very different. Alright, let's talk about the refractory period. Time during action potential and before the next one, when it is difficult or impossible to stimulate the neuron to fire again. Absolute refractory period. No stimulus will trigger a new AP. Relative refractory period. Unusually strong stimulus will trigger a new AP. Let's reread that. So refractory period. Time during action potential and before the next one when it is difficult or impossible to stimulate the neuron to fire again. Absolute refractory period is where no stimulus will trigger a new AP. And then relative refractory period where only an unusually strong stimulus will trigger a new AP. Side note, I've come to find that the best way to study for AP is doing it little by little and doing it over and over and over and over, morning, day, and night. It doesn't have to be a big old long, drawn out study session, just a little bit every single day. It's all about repeating. That's how we remember things. That's how our neurons transfer energy. It's just by reoccurrence over and over again. That's the best way to study. So sometimes I repeat things over and over until it sticks in my brain. Alright, we're almost done, folks. Alright, let's talk about synapses. Signals arrive at the synapse by way of the presynaptic neuron, which releases a neurotransmitter. The postsynaptic synaptic neuron responds to it. So the presynaptic neuron releases a neurotransmitter, and then the postsynaptic neuron responds to it. The presynaptic neuron may synapse with a dendrite, which is that branch-like thing coming off the soma or the axon of a postsynaptic neuron. Neurotransmitters and related messengers. Neurotransmitters are small organic molecules that are released when a nerve signal reaches a synaptic knob. The neurotransmitters then bind to receptors on another cell and alter that cell's physiology. So there are different neurotransmitter classes. There's acetylcholine, ACH, amino acids, monoamines, which are like dopamines. Then you have neuropeptides. A neurotransmitter binds to its receptor for only 1 millisecond, then disassociates. If the presynaptic cell continues to release neurotransmitters, one molecule is quickly replaced by another. Cessation stops adding new neurotransmitters and removes present ones. Alright, let's talk about the fun stuff. Let's talk about neural integration. So, chemical synapses are the decision-making devices of the nervous system. Okay. The more synapses a neuron has, the greater its information processing capability. Oh, okay. So you have postsynaptic potential. Neural integration is based on postsynaptic potentials. Excitatory. Integration is based on postsynaptic potentials. So an excitatory postsynaptic potential, or EPSP, a positive voltage change, usually from sodium, flowing into the cell. Inhibitory postsynaptic potential, which is IPSP, a negative voltage change that hyperpolarizes the cell, usually from chloride flowing into the cell. So hyperpolarization is when chloride is flowing into the cell. Let's talk about summation, facilitation, and inhibition. Some axons may produce EPSPs, while others produce IPSPs. SPs must override the IPSPs for the threshold to be reached. A balance between EPSPs and IPSPs enables the nervous system to make decisions. Summation: the process of adding up postsynaptic potentials and responding to their net effect. Facilitation. Facilitation is one neuron enhances the effect of another. Presynaptic inhibition. One presynaptic neuron suppresses another. So facilitation is where it enhances. Presynaptic inhibition is where it suppresses. We have neural pool and circuits. A neural pool is a large ensemble consisting of thousands to millions of interneurons concerned with a particular body of function. Interesting. Information arrives at a neural pool through one or more input neurons. The physical basis of memory is a pathway through the brain memory trace, in which new synapses have formed or existing synapses have been modified to make transmission easier. That's what I was talking about earlier. How repetition can make the neurons travel faster in the brain. Okay. So, therefore, we have something that's called synaptic plasticity, the ability of synapses to change. We have different types of memory. We have immediate memory, which is the ability to hold something in mind for only a few seconds. Then you have short-term memory. It lasts from a few seconds to a few hours. It's also known as working memory, which allows us to hold an idea in mind long enough to carry out an action. Then we have long-term memory, which lasts up to a lifetime. Then we have declarative memory, which is retention of events and facts that you can put into words. And then you have procedural memory, which is retention of motor skills. Remodeling a synapse or installing more neurotransmitter receptors are involved in long-term memory. Alright, to end, we're going to talk a little bit about nervous system disorders. We have glioma, which is a brain tumor composed of glial cells. They grow rapidly and are highly malignant. Then you have multiple sclerosis, which is where oligodendrocytes and myelin sheaths of the nervous system deteriorate and are replaced by hardened scar tissue. Then you have the Tay-Sachs disease, which is a hereditary disorder of myelin sheath results in blindness and death in children. It disrupts the conduction of nerve signals. Then you have Alzheimer's disease, which is something my grandmother had, which is a degenerative disorder of the brain causing memory loss that can lead to the inability to walk, talk, or eat. Then you have, lastly, something called Parkinson's disease, which is a progressive loss of motor function due to degeneration of dopamine-releasing neurons. All that information was only half my test. Luckily, I did well, but my school moves very fast-paced, and it's a lot of information at once, which is actually really cool. I appreciate that, but sometimes it can be a little bit difficult. I want to make more A&P videos like this. I think they're really fun. I got a really sweet comment on my last video where someone said that it helped them study, and so I really love that. It helps me study, so I should do this more often. Thank you for listening. Thank you for watching, and good luck on your A&P test. Or if you're just watching this for fun, I hope that you have more bragging rights about your nervous tissue to your friends and family. Merry Christmas.